So today I'm going to talk about this ultra-wide neural networks and neural tangent kernels. I'll describe what neural tangent kernel is in the following slides. So the motivation to study the connection between neural networks and kernels really to answer the following two fundamental questions on deep learning. So remember, our goal is to minimize the test loss for any machine learning model. And let's say we have samples, or x and y, from some distribution mu. We want to find a model f, which has some parameters theta that can predict the label well using f theta x. The usual way to analyze this test loss is to decompose it into two parts. The first part is the optimization error. Let's say we have n samples from this distribution mu. And the first term is just measures the error on the training data set. The second term is the generalization error, which is just the difference between the test loss and the training loss. And hopefully, we can find a theta, which is the parameter of this model, that can really minimize both the optimization error and generalization error together. So the two questions is for deep learning is just what are the optimization error and generalization error in deep learning. Okay, so let's look at what the empirical finding of the optimization and generalization errors. So there's a famous paper by Zhang et al. In 2017 called "Understanding Deep Learning Requires Rethinking Generalization." So in their paper, they did a very interesting experiment that they replaced the true labels, the original label from the, some data sets, by some random labels. So now there's no correlation between the input x and the label y. An interesting finding is that they find for both random labels and true labels, the simple gradient method, like stochastic gradient descent, can find zero training loss. Okay? So this is kind of surprising because for deep learning, we know it is a non-convex and non-smooth optimization problem, but simple gradient method can achieve zero training loss, which is a global minimum. So in this talk, I'll use this connection between neural networks and kernels to somehow explain why for both training and random labels, you can achieve zero training loss. So one explanation that why neural network can achieve zero training loss is that our models are highly over-parameterized, meaning there are more number of parameters than the number of data. So for example, for CIFAR 10, we have 50,000 data points, but the state of the models all have more than 1 million data points. 1 million parameters. And for ImageNet, the difference is even larger. So this leads to another problem. It's on the generalization. So again, this is a plot from Zhang et al.'s paper. So they vary the different ratio of random label noise. And you can see that first, the training accuracy is always 100%. But as you increase the number or the ratio of random label noise, the generalization error actually, or the test accuracy actually decreases. This is not surprising because suppose you have all random labels data set, there's no correlation between input and output. So basically, your predictor is just like a random guess. However, from a classical learning theory point of view, the existing theory cannot really explain this simple behavior that, like, for random label, you have a worse generalization error. Because the classical theory are based on, for example, VC dimension. It's kind of the just counting the number of parameters in your model. And because the number of parameters is larger than the number of data points, so all the existing generalization error, like upper bound, is not valid to differentiate the random labels and true labels. And in this talk, I will use the connection between neural networks and kernels to somehow explain, or at least the generalization bound can differentiate the true labels and random labels. Okay? So in this talk, I will first describe what is an neural tangent kernel, or NTK. And I will discuss its implication in optimization and generalization. So in the second part of the talk, I'll describe, although this NTK is like derived for analyzing neural networks, I'll show you that the NTK as a kernel method is also very useful for in practice. So I will show you, for example, using a convolutional neural NTK for image classification, and using NTK for small data sets like UCI database and few-shot learning, and also graph neural tangent kernel for graph classification tasks.
Can you go back to the previous slide?
Yeah.
So, I mean, no theorist would hope to explain this gap of VC dimensions.
Yeah.
You know, and I can list off like 10 other approaches.
Yeah, definitely.
So, anyway, I just want to point that out.
Yeah, this is using the kernel is just one of the ways to explain this difference. There are many other papers, for example, using norm-based bound or pack-based. Yeah, so the kernel is just one of the kind. Yeah. Okay, so to illustrate the main idea, I will just show you a very simple example. So this is a two-layer neural network. The network is parameterized in this form that the first layer we have m weight vectors, W1 to Wm. And m is the width of this two-layer neural network. The second layer is a m-dimensional weight vector, and the output layer. So here we consider ReLU activation function. And lastly, I want to mention there's 1 over square root of m scaling, which is very important in deriving this in this kernel regime. And we consider the L2 loss empirical risk minimization. And we'll consider applying gradient descent on the first layer, W's. So here we only optimize the first layer, just for simplicity. And you can generalize this result to like optimizing all layers together. And we consider this random initialization scheme that the first layer is sampling from a Gaussian distribution. And the second layer is sampled from uniform distribution over -1 and 1. So again, the second layer initialization is just for simplicity. You can use Gaussian initialization for the second layer as well. And the first layer, the Gaussian initialization is kind of standard in practice. Okay, so this is the simple setup. So the key idea to deriving the kernel is that we focus on the trajectory-based analysis. So by trajectory-based analysis, we mean we consider trajectory induced by this gradient descent algorithm. So here, this is a gradient descent on some parameters theta, and it naturally induces a trajectory on the parameters at each iteration. So theta 0 is the initialization, theta 1 is the theta at the first iteration, and so on. So we will also look at the trajectories on the predictions. So here, I'll denote UIT, which is the prediction on the ith example using parameter theta t, the parameter at tth iteration. Okay, so I also denote this UT, which is an n-dimensional vector, which represents the prediction on this n training data points. So it's an n-dimensional vector. So again, because we are using gradient descent, it induces a trajectory on these n predictions as well. Okay. So key idea is actually just analyze the trajectories of the predictions. So first, let me simplify the analysis a little bit. We'll consider the continuous time gradient descent, or this gradient flow, which is just gradient descent with infinitely small step size. So now you can use a continuous process to describe this trajectory. And it's described by this ordinary differential equation, which is the time derivative of each weight vector is just the negative gradient of the loss. Okay? So for this L2 loss, we just expand it one step further. We have this formula. So the negative gradient is just -1 over n times the summation of n terms. The first term is just a difference between your prediction on ith example and your true label. The second term is a partial derivative of the ith prediction with respect to this particular weight vector. Okay, so this is the dynamics of the weight vector. We can also further just use total derivative formula to derive the dynamics of the predictions. For example, for the S prediction, that is time derivative, you can just use total derivative formula to get this form. So again, it has n terms, summation of n terms. The first part is the difference between prediction and the label divided by n. The second term, which is more interesting, is the summation of n inner products. Each inner product is just the partial derivative of each prediction with respect to this weight vector. And you can see that this term only related to this i's example and j's example. So I use this HIJT to denote this correlation. It somehow characterizes the correlation between the i's example and the j's example. All right, so using this formula, we can even simplify the dynamics of the predictions. So we can write it in a more compact form. So the time derivative of the n predictions is the negative HT, which is an n by n time-dependent kernel matrix, with the each entry is defined in the previous slides. It's just the inner product between two partial derivatives. And then you times the difference between your predictions and your labels. So these are n-dimensional vectors. So for our two-layer neural network, actually each entry of this H matrix, there's a formula for that. It's just the inner product between two examples divided by mn times m summation of m indicators, meaning both xi and xj are active on this neuron, or WR. Okay? So just using calculus, you can get these formulas. So the key idea of neural tangent kernel is that we can prove HT, this n by n matrix, is close to a fixed kernel matrix, which is a time-independent kernel matrix. It's called neural tangent kernel, and it first appeared in Jekyll et al.'s paper in last year. Okay? Okay, so let's analyze this H matrix. So let's first look at the beginning. So this is a definition of this H matrix. And remember, we are using randomization for W's. So these are just MIID random variables, and then you take the average, right? Okay, so by that, you can just apply your favorite concentration inequality to prove that this summation of, or average of n random variables will converge to its expectation. Okay? So this is by concentration, we'll get this convergence. In particular, for this indicator and W sampling from a Gaussian distribution, we can actually have an explicit formula, which is this formula. So you can use some invariance or rotational invariance property of the Gaussian distribution to prove this formula. And this is a fixed matrix. It has nothing, it's like time independent. And I'll denote this quantity as Hij star, which is the fixed neural tangent kernel value for the ij's entry. Okay, so this is what happens at the beginning. And now we proceed to analyze this H matrix during the training. Remember, this is the formula. The first observation for this H matrix is that suppose each weight vector only moves a little bit, say epsilon, then actually we can show that only a small portion of these indicators will change from 1 to 0 or from 0 to 1. Then in that case, this H matrix will only move a little bit as well, because there's only a small portion of this indicator changes. Let's say this H matrix only moves like O epsilon order. The second observation is that we can actually show this weight vector only moves a little bit. Okay, so remember, this is the gradient formula for, or the time derivative for this weight vector. And we can just bound the deviation from its initialization by bounding the integral of the gradient norm. The most important thing is that there's 1 over square root of m scaling here, so that the deviation is also in the order of 1 over square root of m. So if you have very large widths, each weight vector only moves a little bit. And it implies that this H matrix only moves a little bit as well. Okay? So to summarize, remember we have this dynamics on about using gradient descent on neural networks. It's characterized in this differential equation. However, we show that this HT matrix is actually close to a fixed one, which is this H star matrix. I showed you the formula before. So this dynamics is actually the dynamics of applying gradient descent on kernel regression using this H star kernel matrix. Okay? So basically what we show is that this is our main theorem, that when the width is sufficiently large, there's a two trajectory. One trajectory using gradient descent for optimizing a neural network. One is using a gradient descent to optimize a kernel. These two trajectories are very close to each other. Okay? So what it implies, so here, this is our main theorem. Let me show you one slice of what is the neural tangent kernel for a multi-layer neural network. So you don't really need to remember the formula. So I want to emphasize two things. First, for an L-layer neural network, the formula for this neural tangent kernel is also an L-layer recursion. So it somehow encodes the neural network's architecture. Second, that has a dependency on the derivative here on this activation function. This term is from using the gradient descent algorithm to optimize the neural network. So it really encodes this optimization method in this kernel. All right, now let's use this CNTK to analyze the optimization and generalization error of neural network. So last year there are several papers showing with parameterization gradient descent or stochastic gradient descent on sufficient wide neural network can converge to a zero or a small training error. So from a kernel point of view, this is kind of trivial because the optimization on kernel is actually a convex optimization. And you can definitely achieve the global minimum. And the global minimum achieves zero training loss as long as this kernel matrix has a lower bounded eigenvalue. Or you can say this kernel is somehow universal to fit any function. Okay? So here we only consider the quadratic loss. You can also generalize to other loss functions. So you can check these papers. So that's for training. For generalization, for kernel, there's a direct, so because we show these two trajectories are close, it basically implies that the final predictors of the kernels and the neural networks are close as well. So in that case, we can just use existing kernel generalization bound to analyze the generalization of the neural networks. So here, this is a data-dependent kernel generalization bound. So it depends on your training data. So it's y transpose h star inverse y divided by n. Then you take the square root. So this holds for basically any kernel regression. So we use this generalization bound to see whether this generalization bound can really differentiate the random labels and true labels. So here on MNIST and CIFAR data set, we vary the different portion of random labels. And this blue line is our generalization bound. And green line is an L1 loss, and red line is classification error. So you can see that at least this generalization bound can differentiate these true labels and random labels here. Okay, so somehow explain some generalization behavior of neural networks. Okay, so now I'll proceed to talk about really using this neural tangent kernel in practice. So first experience we try is for convolutional neural tangent kernel because we know neural networks are successful on image data sets. So the formula is very complicated, but in short, if you want to compute the kernel, you take two images, x and x prime. And in the first L-1 layer, you will output a P by P matrix, where P is the number of patches in this image. And you can compute this via dynamic programming approach. You can check our paper for the details. Now, for the real output of this kernel, there are two choices. The first one is if your original convolutional neural network is just a fully connected layer for the last layer, so you just take the trace of this P by P matrix. Another choice is to use global average pooling, which is a very popular and powerful layer. In that case, if your CNN uses global average pooling, then the corresponding kernel, you will use the summation of all the entries in this P by P matrix. Okay, so derivation, for the derivation, you can just check our paper as well. So let's see what happens in practice. So we tried this neural kernel, convolutional neural kernel on CIFAR 10 with different depths. And we compared with CNN. So for CNN, we use a SGD with small learning rate, and we turn off like batch norm, weight decay, and other tricks. So you can see that CNTK, especially if you use global average pooling, gives a reasonable performance on CIFAR 10. The best performance, like 11-layer CNTK plus gap, it achieves like 77% accuracy. Definitely, there's still a gap between convolutional neural network and CNTK. So it might comes from we are using the finite width for CNN, or this SGD has some magical like effect on the generalization. And an interesting finding is that this using global average pooling improves both convolutional neural network and convolutional neural tangent kernel. So this somehow illustrates some like architectural benefits of neural network can be transferred to kernels as well. So this global average pooling kind of interesting, so we investigate a little bit further. So in our more recent paper, what we find is that why global average pooling works. Because at least for CNTK, we can actually show that CNTK with global average pooling is actually equivalent to using CNTK without global average pooling, but with a full translation data annotation. So here, by full translation data annotation, I mean you take an image, you translate the image a little bit, and then you put the new image and the original label in your training data set. So that's one form of data annotation. And for full translation data annotation, you just consider use all the possible translations. So the proof of this theorem is super easy. You can just check the formula, and you can find that CNTK is invariant under this translation operation. And so for full translation data annotation, we also find some problem. For example, so this is a track from CIFAR 10 data set. Because you are considering all possible translation, you may create some unrealistic images. For example, for this image, basically you cut this track by half, and you put the bottom half on top of the top half. So this image is like kind of unrealistic. So again, in our paper, we somehow fix this issue. The idea is that we just use some local information of this track. Okay, so we just one line change of this convolutional neural tangent kernel. Originally, we just sum up all the entries. Now we put some weight of each entry, and we use this weighted average to output the final kernel value. Okay, so this somehow captures the local information of this kernel matrix. So this one-line change actually directly improves the convolutional neural tangent kernel from 77% to 80%. And furthermore, with some additional tricks, for example, there's a horizontal flip data annotation, and there's a random patch preprocessing technique by Coase et al. In 2011. We can achieve 89% accuracy on CIFAR 10 data set. This actually matches the performance of XNet. It is actually the best method we know of that is not a neural network. So this local average pooling idea, you can also use it for convolutional neural network. It also corresponds to a certain layer in convolutional neural network. So you can check our paper for the detail. So another experiment we try is on the UCI data sets. It's kind of classical or traditional data sets. So we tried on 90 small classification data sets from this database, ranging from different domains. And so this paper in 2014, they compared 100 classifiers and on this UCI data sets. They found that random forest is the best one. And the kernel also is very strong, like Gaussian kernel is the second best. So our experiments actually inspired by this Olsen et al.'s paper in 2018 that they tried this over-parameterized neural networks on this UCI data sets. And they found that neural network gives reasonable performance on these data sets, but it's not as strong as random forest. So yeah, we just want to try NTK because NTK has some benefits over neural network, like there's no randomness in initialization and training, so it's kind of more stable comparing to neural networks. So here's our results. So we compared different metrics to evaluate these different classifiers, like average rank, average accuracy, and P90 and PMA, their definitions there. So basically what we find that NTK is actually a very strong classifier on this small data sets. So it's on different metrics, it's actually the best one. Even it not only beats neural networks, it also beats random forest, which is like the gold standard according to the 2014 paper. So in our paper, we have more results, like pairwise comparison with different classifiers, and the code link is here. The main message is that this NTK can should belong to any list of the off-the-shelf ML methods. So if you have any like new data set, you can just try NTK and see its performance. Okay, another experiments we try is on this few-shot learning, where the setup is that we take less than 50 trained on ImageNet, and we use so less than 50 have several blocks, 5 blocks, and we use the outputs of these blocks as feature extractors. And then we try few-shot learning on VOC7, which has 20 classes, and each class only have 1 to 8 examples. So the standard practice is just, okay, first use this extracted features, then we train a linear SVM on top of it. So we just try NTK, and here we try convolutional NTK because this is the image classification task. Okay, so here is our result. So we just replaced linear SVM by the convolutional neural network kernel SVM. So you can see that just replacing this replacement actually improves the linear SVM using just 1-layer convolutional neural network kernel. And sometimes like 2-layer convolutional neural network kernel gives a better performance, but usually just 1 layer is the best one. Okay, so it somehow shows, at least on this few-shot learning, you can just use this like CNTK as a drop-in classifier to replace the original or standard linear classifier. So lastly, we also considered graph neural network kernel for a graph classification task. So recently, graph neural networks were hot, like used for graph classification and other tasks. So basically, you have a graph and you have some label. You want to train a neural network to do classification. And for any given graph neural network, we can also derive a graph kernel. And we tried this graph neural network kernel on several data sets, including some chemical data set and some social network data sets. And we find that on this data set, actually this graph neural network kernel gives better performance than the previous methods, including graph neural networks and graph kernels. Okay. So in summary, we can use this neural network kernel for understanding neural networks, its optimization and generalization behavior. And we can also use it for understanding the benefit of certain architecture, for example, global edge pooling. Of course, there are many open problems, like NTK cannot really expand the normalization technique now, like for example, batch norm, weight norm, group normalization. And the finite fits actually sometimes give you some benefits on generalization, at least on CIFAR 10 data sets. And we don't have a good understanding of it. And the learning rate in SGD is actually very important. And there's a recent paper by Yuanzhi, Colin, and Tengyu showing at least on some data sets, using a large learning rate at the beginning really helps generalization. But the general phenomena is still an open problem. So these are some open problems. And lastly, I want to emphasize again that this NTK is very useful in practice. So I have tried on UCI datasets, few-shot image classification, and graph classification. And then I believe that in other domains, NTK can be practically useful as well. And these are some references, and I'll conclude here and take questions.